within PVT of fluids. So we look a little bit into gas condensate calculations. I'm not sure if you already have started working on that with a student assistant. You probably have touched exercises on that too. But so there is not a big difference between, at least for the calculations when we are above the dew point for the gas condensates. And then we look a little bit into equation of states and cubic equations of states. And that's what the calculations are based on when we are doing in reservoir simulators. We will not go deep into it, but it's nice at least to have some ideas about what's being done when we are working with a PVT simulator and how to do the calculations. So that's the plan for today. And as I said, last week you had some exercises, problem solving with the student assistant, and that's the plan for the next week too. So this, as I said, this will be the last lectures on PVT of fluid. So now we concentrate on problem solving and prepare for exam. And sorry.
Professor, can I ask something? I think you mentioned before that we were going to receive potentially examples of previous exams.
Yeah, so the plan for the student assistant is that he is going to go through 2 exam sets. So that's the plan. So when you have finished the problem solving on exercises, he will introduce 2 exam sets and sketch solutions for you. So that's the.
Okay, thanks.
Did I answer your questions good enough? I hope so. So that's what we have planned. So if we go further down, and as I said last time, 2 weeks ago, that the exam has. The date of the exam has been changed to the 25th of November. Hope that's not a problem for anyone. It was due to.
Why? This is, you changed the.
I didn't change anything. It's the exam office at the faculty that had to change it because there's a lot of students that have this at the different specialization and in different master programs that has this as an obligatory course. So it's not only the people who is linked to petroleum master in petroleum engineering that have this course. So there was students that have a collision between other obligatory courses and some of these. So it was more difficult to change the other obligatory courses. So that's why it ended up. But I think most of you will prefer to have it in a little bit earlier than close to the Christmas. I hope. So as I said, it's a digital exam. It will be so you can do it from home. And the time is from 9 o'clock in the morning to 4 hours from then. That's how it's done. And you write your answers on paper and you scan take photos on each individual page and compose it and send it to deliver it digitally, the exam. But I think you will get introduction. If you not already have got that, you will get the introduction to this, how they are solving digital exams. So be aware, you need to use your camera on your mobile phone and scan your pages. So that's the plan. So from 4 hours is set for the exam, and I think you have 30 minutes to finalize the delivery. So you can, you may also be able to take a picture of yourself smiling. Hopefully you are smiling.
Does it have an extra grade or something like that?
You never know. You can try. So you never know. I haven't been doing digital exams before, so it was done last semester. But last semester my subject was oral exam. And everyone was smiling through Zoom. So all the candidates were smiling, at least in the beginning. Okay. So as I said, gas condensate is on the plan today. And from previous, we know what the gas condensate is. We have reservoir conditions, reservoir temperatures that are to the right of the critical point, if you look at the phase envelope in a pressure temperature diagram. And so typically, reservoir pressure could be above the dew point, and we are going through the dew point and into the two-phase region of the reservoir during production. That's the typical way to produce gas condensate. Pressure maintenance by water injection is not typically what's being done with gas condensate. Don't ask me why not, but because I don't know the reason behind it. But it's probably cheaper to produce it without pressure support. And the industry is always choosing doing it with the lowest cost. So that's the way it's done. And so that's our gas condensate, and as we go into the two-phase region, we will have liquid dropout. And that liquid is typically lost forever. That's something that we are not producing back, because the volume of liquid is typically lower than the residual oil saturation that you will have for these systems. If you have rich gas condensates and the amount of liquid that could precipitate start to reach 25%, or then maybe there are mobile liquid phase within in the reservoir during the pressure decline. But typically it's lost. We'll come back a little bit on that, but how they are often approaches production of rich gas condensates on the last slide today. Okay, so what we know, and we are going to do calculations based on gas condensates, and typically what we have, we produce the gas through the reservoir fluid through a separator system, and the fluid that we are producing is the gas phase. The fluid from the reservoir is the gas phase. And as I said, and for pressures above dew point, it's the same calculations that are done as for wet gases. It's a single phase fluid that we are producing. So we produce always a representative fluid of what's present in the reservoir. But as soon as we start to go below the dew point, we start to precipitate liquid, and the composition of the gas that we are producing is continuously changing as the pressure is declining. And that makes the calculation more complex and difficult. But there are approaches on that. And typically what we need in calculation, we need the BO factor and the BG factor, and we need the gas oil ratio, and that we can get from separated or from production data. Important input parameters when we need to do calculations. And as I said, as far as when we are above the dew point, it's the same approach as we have done for gas. When we looked at calculations for reservoir fluid that are gases, and we are using the equation of state that we can use as an approach when we do the calculations. And you have here you can look into the chapter L11. There is an extra sheet that we can be practical to have. If we have the composition of the fluid that are produced, we can in a way predict the pseudo-critical temperature for the C7 plus fraction of our fluid. So for compressibility factor calculations, if we have chemical analysis, we know the composition based on the C1 to C6 components. We can take that from table values, but we need the critical conditions for the C7 plus fraction, and that we can take from this table when we have production data available. And then we can calculate the pseudo-critical temperature for the whole system from C1 up to C7 plus. So it's in a way the same approach, and then we pick all the set factor from figure 8.4 based on pseudo-reduced temperature and pseudo-reduced pressure. There's a simple approach on doing that. And as I said, we have looked into that previously in calculations on gases. If we don't have a chemical composition of the produced fluid, then we can predict a pseudo-critical temperature and pseudo-critical pressure for the gas produced if we know the gas gravity of the produced fluid. So if you have a gas gravity, we can go up, and we go up to where we have a gas condensate fluid, and then we go to the left and we get the pseudo-reduced temperature. And if you go further up to the line for the gas condensate, we can get the pseudo-critical pressure. So pseudo-critical temperature and pressure for the systems is given by short figure 8.6 in the gas chapter. And then we calculate the pseudo-reduced pressure and temperature for the actual pressure conditions in the reservoir. And then there is an empirical correlation that was developed by Reza and Katz back in 1948. And these charts give us a gas gravity ratio of gas gravity of the well stream vapor divided by the gas gravity of the surface gas or the separator gas. And that's based on input parameter. I need to know the gas condensate gravity in API, and I need to know the gas gravity of the fluid. So if I have a gas gravity of 0.6, 0.7, or 0.8, and then I can predict well fluid gravity divided by the trapped gas gravity for a certain BO factor for the system. So this is the inverse of the BO. And there is also a correction, or you can catch if I know the API of my liquid phase produced, I can also predict molecule weight of that liquid from this chart here. So when we are doing the calculations, definitely we can look a little bit into how to calculate PO and VG from production data. And this calculation is only valid when we are producing lean gas condensate. So with only gas phase that are produced to the well. So and that's, as I said, it's in a way based on the same calculations that we did for wet gases. The number of mole of stock tank oil, that's the mass of stock tank oil divided by the molecule weight of the stock tank oil, and I can express the mass as density multiplied by volume. I can also calculate, if we had the previous, in the previous chart, we saw that there was molecule weight here. I can also, there is also a formula, Gray-Gauss formula, that is developed for molecule weight for gas condensates. And that's also given in the formula sheet that you will have to the exam. So this 6084 divided by the API minus 5.9 should give you a good estimate of the molecule weight for a gas condensate. So the number of, so I have the calculate, I can express the number of moles of stock tank oil. I can express the number of moles of gas produced. And that's the volume of gas at standard condition divided by the molar volume for the gas. The constant. And the total, the number of moles should be then be the number of moles of stock tank oil plus the number of moles of gas. And I can use the equation of state, put it into there. And if I have working with 1 standard barrel of stock tank oil, the volume of gas at reservoir conditions is equal to the BO factor. And if I need to, the gas, the typical gas condensates, they have a BO factor that is going from up to 12 for a typical gas condensate reservoir. While when we will work with the oil, with dissolved gas, the BO factor is typically going from 1 up to 2.5. So you have a 10 times, typically 10 times higher BO factors. And the volume factor of gas is then the volume of gas at reservoir conditions divided by the GOR. So that's in a way, and that's the same calculation as we do for wet gases when we are above the dew point for the gas condensates. And if you look at the BO factors of what we see from initial pressure down to the dew point pressure, there is an increase in the BO factor, and then it typically declines again as we go into the two-phase switch. So that's a typical trend of how the development of BO is through the production system. Yeah, I think that's what we need to say about that. Another approach is also an empirical correlation by Sage and Old, where they also have developed valid for gas condensates. We can also calculate the formation volume factor, here expressed as a U. Then we have pressure, temperature, and gas oil ratio available. And there is a empirical correlation, the A here, that is in this tabled value. And the table is also given in the compendium in chapter 11. So it's an easy approach to get a reasonable good value if we are lack of other data. So in early stage calculations, when we need to know a little bit about the properties of the fluids in the reservoir, this is a simple approach, and it's typically often done for estimates. And then in the compendium, there is an example. I will not go in detail on it, but this describes a little bit also how we can get use of this correlation by Vesa and Katz for doing calculations that are linked to BO or volume factors. Good. So if you want to look at it, you can probably, it's better to look at the example in the compendium than it's in these slides. But I put it in for if people are not reading the compendium. So yeah. So I don't plan to go straightly through it. You can look a little bit on the problem here in exercise, and then you can look at where they're taking in the numbers and they do calculation of the average density of the gas. That's linked to the amount we produce multiplied by the of gas at individual pressure stages, separator and standard conditions, and then the density is multiplied and summed up. We can calculate the average density of the gas from the individual pressure stages. And from the production data, we can also calculate the volume of stock tank oil divided by volume of gas. And then we get the BO factor. That was used in this here. This chart here, so a BO factor close to 8 or volume factor close to 80, and then we go up and we pick a difference between density of the well fluid divided by the trapped gas. But you can look a little bit further into the example by yourself. I think it's a good learning to test out and try to understand what's going on. And it's a little bit better description in the compendium than it's on these PowerPoint slides. And definitely, reserves and recovery calculations are important, and initial gas in place, initial oil in place, is always something that we need to evaluate in the early stage when we have a reservoir discovery. Important values when decisions are going to be taken if it's possible to build out and have a earning from producing the reservoir. And hydrocarbon pore volumes is the bulk volume of your rock multiplied by the porosity, average porosity. That's typically given by the geologist based on the analysis that are done. And there are also laboratory analysis that add up to the initial water saturation based on core analysis to information that are given from well logs.
Sorry to ask that. When we were talking about the core analysis to obtain the initial saturation of the water. You're talking about the regular core flooding. Am I right or wrong?
No, it
isn't like that?
No, it's a Dean Stark analysis.
Dean
So
Stark.
there's a
Yeah.
specific analysis to catch the water that.
Or you can just put it inside the core flooding machine and put the.
Yeah, but you always need to. You don't know the porosity. You need to have a good mass balance.
Yeah.
So that's often problem in core analysis. So what they are doing, they extract all fluids out of the.
Wash it completely.
And then they use Dean Stark as an analytical method to quantify the amount of water, and that also quantify the water that is dissolved in the liquid in a hydrocarbon phase to get the absolute value of the water present. Sorry, sensitive modes here, so suddenly I jumped a little bit out of. So initial gas in place is then definitely we can calculate that by the total number of modes inside the system. And I introduced a V here, that's the mole fraction of vapor and the molar volume of gas. And the total number total number of moles of liquid is expressed by the equation of state. PV equal to Z and RT. So solve it by the number of moles. And the initial oil in place is then the molecule mass of stock tank oil divided by the molecule weight of stock tank oil. And then we have the number of gas initially in place multiplied by the liquid fraction of the mole fraction of liquid. And the number of moles of gas is the same as we see here, expressed by the equation of state, the real gas law. And then there is and the recovery calculations when we are producing the reservoir from the initial pressure down to the dew point pressure. I can calculate the initial number of moles in my reservoir, and I can calculate the initial number of moles of gas at dew point. So the delta produced number of moles will be the number of moles of gas initially in place divided minus the number of moles of gas at dew point. So that's typically recovery calculations that can easily be done as long as we are above dew point. And the volume of gas is then is produced is the number of moles multiplied by the mole fraction of gas multiplied by Vm, and then we have the stock tank oil. The volume of stock tank oil that will be produced is the volume of gas at standard conditions calculated here divided by the GOR. And then there is a third approach to try to calculate what's happening when we are moving from dew point and into the two-phase region. So that's what we are going to. So that's what we are looking at here. So if I look at my reservoir, I can in a way link what's happening in the reservoir to what was done when we are doing a constant volume depletion experiment in the lab. And that's what we are doing. When we are going to calculate beneath the dew point, the easiest way is to, and actually the only way is to look at the laboratory data from the constant volume depletion. So then we can just say that the gas produced at a certain step in pressure, when I'm going from P pressure J minus 1 to Pj, in that step, I can link that to the volume of gas I have produced from my PVT cell at pressure step J, divided by the volume of gas I have in my PVT cell at dew point. And then this can be expressed as gas produced at step J. And I can put up a ratio between the moles produced in the cell and in the reservoir. And then we have the number of moles at well, sorry, I can express this as, if I want to have the gas produced, I can use the real equation of state to express the number of moles at the dew point and at step J. And if I simplify the equation, I end up with this term here. And the number of moles produced at step J will then be gas produced at step J multiplied by the molar volume. And this is expressed then further like this. So there is a possibility to do these calculations also beneath the dew point, or at least good estimates of the production. But it's definitely in the reservoir we have infinite number J's in our reservoirs. But in the PVT cell in the lab, we just do a certain number of pressure stages. But it gives us a good estimate of the expected production as the pressure declines in the two-phase region. Yeah, and then we can simplify the production definitely regarding the number of moles that are produced. What we can say that the gas production is only linked to the components up to C4. And all components from C5 and upwards is linked to the liquid fraction. It's just we need to estimate our production, and that's an easy way to approach it. Simplify but it's more accurate than not to doing it or not have any input data. So that's what we can do, and then we can get the vapor fraction the molar fraction of vapor. And we can get the expression for the fraction of liquid at step J based on that approach. And then we can express the volume of Stockton coil and the GOR for the individual systems. Yeah, by the additive volume method. And as I said, if the shift should be at normal C4 or ISO C4, I'm not sure, but this is typically what they are doing, and it's probably based on experience. So the gas that we are producing is the IE composition in the system. So that's why we are putting sum up the gas fractions of the individual components. Yep, I think that's how we could approach calculations beneath the dew point. And then we can put everything here up in a table and sum up the individuals. Each step, pressure at each step, you have the number of moles produced at each step, the gas produced at each step, the volume of gas at each step, the volume of stock tank oil at each step, and then we take the cumulative components, sum them up, and then we have the production as the pressure declines. Other parameters that are affected, so typically what we see, if you have a lean gas condensate, we have the SOR less than the oil saturation is less than the residual oil saturation, so all oil that are precipitated in the reservoirs are retained. So we have a GOR typically going from constant values from initial conditions to dew point, and then when we go into the two-phase region, the GOR is increasing.
Because at that place, which is constant, no gas is producing, so we don't have.
Yeah. No, it's the same here.
It is the same.
Yeah, the same fluid composition of the fluid always above dew point. So no change in the composition. But when we go into the two-phase regions, we start to change it. So more gas is produced and less oil is produced when we go into the two-phase region, because we precipitate the heavier components. And what we see then is that there is a liquid production that precipitates. We see that the liquid, so typically what we see is that it precipitates and volume of liquid increases to a certain pressure, and then it starts to decline again. So the gas phase, the heavy components then start to evaporate and go into the gas phase again, and the pressure is declining. And then we have relative permeabilities that try to describe this fluid. So if it's a relative permeability against oil saturation, so when you're producing this gas condensate, we are actually going from low oil, so we're going from here and in this direction. Yeah. Okay, so this is in a way trying to describe the production, how this affects the important parameters in the system during the production into the two-phase region. Rich gas condensates, typically you should have a liquid dropouts typically up to 25%. And I'm not sure how many of these reservoirs that really exist. You see, for me it's a little bit funny. Typically maybe 10% of all hydrocarbon reservoirs are gas condensate. But if you look into the focus in research that are being done, it seems that 90% is done on gas condensates. So it's probably because it's still possible to do some calculations. It's not so complex that it's getting difficult to do good estimates. So to improve calculations, there's still opportunities on gas condensates. And improve the models that we are using. Come back to that in going to the next chapter here on equations of states. So typically for rich condensates, we need, if you are going to do any calculations, it's getting so complex that we can take benefit of the simulators to do reliable calculations. But for rich condensate, there is one possibility to improve recovery, and it is gas cycling. So what you're doing, you take a methane or a dry gas and then inject it into your rich gas condensate. So you increase the solubility of higher end components in the produced gas phase.
Of course, it's miscible injection.
Yeah,
Am I right?
yeah, it's a miscible injection. Yeah, correct. So you say in a way, but it's just it's a good way to describe it. So if that's how that is from an energy point of view, if that's I'm a little bit skeptical because gas injection is energy demanding. So but this is something that is being done and have been done, but into which extent I don't have a good overview of that. So typically what we are doing, typically above dew point, so we are increasing the solubility of gas and reduce the potential of precipitation of liquid when the reservoir are going below the dew point. Yeah, so that was in a way the calculations on gas condensate that I wanted to introduce to you. In the exam sheet, the last page in the exam sheets will be a sheet containing the information about the formulas that you need for calculations. I mean, there are something on temperature, pressure, density, and that sheet is specific density, API, how we calculate that. We have a density, gas gravity, how we can calculate that. And we have this Gray-Gauss formula that was given for molecule weight of gas condensates, if that's needed. We have all these volume factors, barrel, cubic feet, how much that represents in other units, US gallon, and the US gallon is what we are using in oil field units. Gallon, that's the imperial gallon, but it's not normally used if you are not in England. Molar volume of gas in standard cubic feet per pound mole, or in cubic centimeter per gram mole, or cubic meter per kilomole. We have a SAT factor for air, we have molecule weight of air, and we have the gas constants given. So for most calculations, everything should be available there.
Professor, can I ask a question? I tend to be confused with the combination of units, like the compatibility of them. I'm just wondering if that bottom section, the gas constant, is summarizing basically the groups of units that are, yeah, I mean, besides telling the gas constant, it's also summarizing the units that are compatible to each other, I guess.
When we are working with oil field units, it's typically 10.732. That's linked to oil field units. And I think most calculations that we are doing is linked to this constant. Yeah. Yeah, this one. So we are typically in SI units, we are working with the cubic meter.
Right.
Yep. So that was the parameters that will be in the sheet. Yeah, the next, so we take a short break and then we'll continue on 10 minutes break, and then we'll continue with looking a little bit into this equation cell states that are used in the reservoir simulators, more or less based on van der Waals equation. Yeah. With a group of van der Waals equation of states. Yeah. Thanks. I couldn't see it. There's something. Okay. So back one slide. No, that was okay. So everything is based on the corresponding state principle in a way with regarding critical point approach to calculate the parameters that we need. But the equation of state is in a way with ideal gas law, and then we have a set factor that we compensate for the changes from the ideal gas law. So that's the compressibility, and then at the volume, so we can calculate it based on critical point or critical state, probably a better way to say it. So I can express the volume as a set multiplied by RT divided by P. So then I have a pressure volume diagram instead of what we typically are using, easy to explain pressure temperature, because temperature is constant in the reservoir. So it's easier to understand a pressure temperature than a pressure volume diagram. But for an ideal system, if I go through the critical point, I have a temperature curve, a isobaric temperature curve, same constant temperature. If I go into a two-phase region, I will have a constant temperature like this. And I can also calculate volume fractions based on at the individual volumes here. And I'm going through the two-phase region. For an ideal system. In the reality, these are not straight lines. But this is the ideal approach. And if I want to go from volume, I can easily also go into SAT instead and express it instead of volume. I express it as a SAT factor, the volume. So what you see here, volume, I can express the volume by the SAT, or I can express SAT as a volume parameter. The opposite. So that's often also done if I'm going to use the equations of states to calculate the SAT factor. And as I said, there's a lot of different equations of state that has been developed. And we are going to, when we are calculating petroleum fluids, we are using, most of the activities is linked to the van der Waals family of equation of states. All the other ones here is linked to other type of fluids. So what fits best for the hydrocarbon fluids is, as I said, the van der Waals family of equation of states. And there are different things that have been developed over time, but it started with van der Waals. And what we are doing in a way, we need to have equation of states to explain, to be able to calculate. And what they have preferred to do is to have equation of states that can easily be solved. so cubic equations of states is in a way the approach. So van der Waals can be expressed as a cubic equation of states, and then there are roots. When we solve it, we can find the roots, and we can toggle with that and say that this is a root that is out of the system, but we have other routes that give solutions to the problem. And if you look at PV is equal to RT for 1 molar of fluid, then the pressure is expressed. We have added a term to the pressure, and we have added a term to the volume. Huh?
Deducted 10. Okay, okay. Yeah.
Yeah, we have added 1 term to the pressure and 1 term to the volume to compensate for that they don't behave ideally, these fluids. Or I can express it as a pressure equal to, based on this, where we have that the V is the molar volume. So I'm working with 1 mole of fluids, and A divided by V in second is correction for intermolecular forces, and B is correction for volume occupied by the gas molecules. So in an ideal gas system, at low pressures, and at low pressure, most gases behave as ideal system, but as soon as we start to compress them, the volume of the gas molecules in the total volume start to, we have to account for that. And that's done by this B factor. Yeah, so that's in a way the approach of trying to solve it. So, and if you look at the so this is the van der Waals equation. He developed it in 1873. Further developed by Radlick and Kwong, so he improved it a little bit. So what he did, he added temperature as a part of the equation. So we also take temperature into account. That's the main difference from van der Waals. But still, there is a compensation for volume and compensation for pressure. And then
What's the name
Radlick Kwong, Radlick Kwong. So that's the SRK. So you have the RK equation, and now it is a Swash further developed the Radlick Kwong equation, and he added a new term here on the same for the volume of molecules, but he improved the term here linked to the pressure. And then there is so this is the 3 main equations that are used in calculations today on hydrocarbons. It's the Swan-Radlick-Kwong equation, is the Peng-Robinson equation. You see there's a small change on the term here for pressure, compensation for pressure. Third equation, that is Penelux. And everything here was done in the 1970s and early 1980s. And we are still suffering with the same equations. So this is in a way, I tried just to put up how the equation could be used in an analytical form to what are we adding to the system to try to do the calculations. Just to give you an idea about them, and it's an idea of what's happening also in the simulator. So I start with this pressure, express the equation based on pressure, and A and B are found from pressure-volume relationships at critical points, using this pseudo-reduced pressure approach and things like that. So then I can calculate my values for this constant, A and B. the B. That's what everything is about, to find the values for that. And so what they have done, they said that the AI for the individual components, so we need to separate them into the contribution from each individual component in the gas. And then they have introduced an alpha I. The parameter is, and the alpha I is in a way an expression of the an M factor. The M is expressed as the interaction, the shape of the component. So the omega is a factor that describes the sphericity of the molecules. So if it is completely spare, it is the omega is low, and if it start to become non-spherical, it's then the omega is increasing. So you see low values here, increased values as we go up from C1, very low value for omega for C1, and then we go to normal C6, a long chain is not spherical anymore, the molecule, and then we need to compensate for that. So it's a physical parameter trying to describe these components, and it's an approach, but it's probably not the best approach, but it's a simplified approach to try to describe how molecules behave in between each other, but as a physical parameter. Yeah, so that's in a way what they are doing. So we add the omega to the system, and then we try to express or the A and B. So A and B at the end is calculated. There is sum up different components and the mixtures, how they follow each other. Set and set J are mole fraction of component I and J respectively. And KIG is a binary interaction coefficient. So they add an extra binary coefficient also to the system. So and in the Benelux term, they have added not only A and B, but they have added C as a new parameter to improve it a little bit better. So the Benelux equation is able to handle liquids a little bit better. Liquid estimations a little bit better. So that's the way it's done. And this is in a way this binary interaction coefficient also added to the system. How individual two molecules interact with each other. That's what they're doing. So nitrogen interact differently with CO2 and H2S compared to nitrogen, compared to methane, ethane, propane. So that's what they try to do through that constant.
It depends on the molecule, coefficient.
The interaction between, it's typically the interaction by the non-hydrocarbon component. So hydrocarbon components, they like each other and and behave correctly. But if you have inorganic components, they have a different interaction.
So if there is only hydrocarbon present.
Yeah, then this coefficient is not needed. I think.
Zero.
Yeah. Yeah, then it's set to 0. Yeah, that's correct.
If you had something else, for example, MgSO4, does it happen for that?
For what?
For the interaction you
What type of component?
For example, the component you said, okay, hydrocarbons do not have any problem with each other. But if you have something from outside, like, for example, H2S or SO4. I'm talking about
Yeah,
the
but
coefficient.
SO4 is not a gas.
Yes. I'm talking about the solid. So it is not working for that?
No, the equation of strength is used for also
For
the
gases.
C7 plus fraction.
Yes.
Be aware of that. And everyone understand that
We don't
the
have something-
complexity is everything is a guess, and that's why when we are doing, and that's what we are doing with PVT simulators.
Yeah.
We are tuning the simulator at the end, because even though we put in A and B and C, and if you have put it D and E and F, it still would fit.
You don't have a gas at that.
Yeah. So you have at the end, even though we try to compensate the model, it don't fit. So at the end we need to fit it against the experimental data,
Yes.
and then it fit at the conditions for the experimental data, but probably not at the pressure above and the pressure below. So you tune it, and you try to tune your simulator at the conditions that fits best for what you are going to work with, the conditions you are going to work with. But the ideal, so there is no ideal solution for calculating hydrocarbons fluids. But we can, based on the SRK or this equation of state, we have a good approximation, and we can tune these simulators so they behave as we want them to behave, based on experimental data calibration. Yeah, so that was in a way the hopelessness of equation of states. No, it's not completely hopeless. It's better than the real gas law, definitely. and equation of states, the real gas law, with how we compensate with the reduced pressure and temperature and calculate SAT, that's valid, and it functions quite well when we are not close to the critical point. But as soon we are moving towards the critical point, that equation is also off. So this SRK equation and it's much better close to critical points for calculations. So if you are working with fluids that are volatile oils and things like that, it's better to use these equations compared to a simplified approach with a real gas law. So that's in a way what we are doing. So next week, exercises, problem solving, preparing for exams. And
you won't be there?
Huh?
You won't be there the next session?
Maybe if I have time, I will be there. But we'll see what's happening. But I think so. I had a talk with yeah, and I asked him. He was one of the best students last year. And he said he never learned any his skills on PVT has dramatically improved as being a student assistant. So there's always a hope to learn it next year as a student assistant. Okay, that was the plan for today, and so I will probably try to have close to the when we are in November. We probably invite for a general meeting for questioning and things. Maybe both me and Siri will probably be available. So that's the plan. I'm not planning to do. Go through everything, the slides once again or something like that. No, I don't think. I think you should concentrate on problem solving and maybe look into previous exams.
So that means next week is our last day.
No, I think so when we put up the plan. Sorry, page up. When we put up the plan, there is week 45 that is probably also we can have some activities. So if we are going to have a summary session, it will be probably in week 45. But no, the exam has the date of the exam has changed. So we are now closing to the exam date also. So I can't remember what date is week 45.
17.
It's 17th.
And then is the next
So then the exam is the next week.
Yeah.
So definitely it will be a short summary. Okay, so that's the plan. And the plan is that we are more or less finished with the lecturing. Good. Anyone on Zoom that need to add questions or have something they worries about? You don't have any shoulder to cry on, as the one is in the lecturing room? Anyone else? No? Okay, but then I think we end the session. Or something funny with the dance.
It's so fun.